Hello, everybody. Welcome to Endgame. Today's topic will be about machine learning and AI, with your host today being Popopo and Great Blonde Elf. Let's have some fun.
Yay! Thanks,
That was
Skeleto.
great.
Yeah, I appreciate the introduction. Hello, everyone, and welcome to Endgame. Tonight, I am joined by great guest host, Great Blonde Elf, aka Sean Robinson, who has joined us here today. Kind of new to the VRChat community, so welcome as well. And why don't you tell us a little bit about yourself and what your background is on this topic?
So everybody, first of all, thanks for being here. My name is Sean Robinson. I am currently the head of artificial intelligence for a startup studio in South Seattle. Call out to Seattle. I actually come from the computational physics background. My PhD was originally in computational astrophysics, and I parlayed that over into a stint at our national laboratory structure for about a decade, working in, first of all, the area of computational nuclear physics, and then gradually, as time went on, and I'll describe some of this today, going from what I call low parameter space to high parameter space models, as machine learning started to take over and as the edge of modern artificial intelligence started to take hold. So for the last 2.5 years, I've been leading a variety of machine learning artificial intelligence efforts here in Seattle. So I'm honored, humbled, and happy to see you all.
Well, that's awesome. So you're fully immersed in this space. It sounds like your whole career has like you didn't start off focusing on this stuff. It kind of like was a natural path that took you here, though.
Yeah, that's absolutely the case. I mean, basically the way that I like to say it, and I'll bring this up in a minute, but I like to say machine learning is relatively well described, and we'll talk about it, but artificial intelligence is the really interesting term. Artificial intelligence, I like to say, is whatever 5 to 6 years ago we said, computers will never do X. Well, it turns out that for a long time, artificial intelligence research has been exactly what people said computers will never do. And that meteoric, dramatic explosion of capability is kind of what brought a lot of my co-researchers here to the field, and what brought me to the table. Essentially, there were always been numerical methods, numerical recipes, and there have always been simulations, analysis, and modeling. But what we're seeing right now is an absolute detonation in the capabilities of humanity to solve really abstract, really difficult problems in a space where we didn't have models before. So that brought me, it brought a lot of my coworkers. It may actually bring some of you to the field if you have that interest. And if you want to talk about that, please, I'll hang out afterwards. But I could not be more bullish on the technology. I guess I'll say it that way.
Excellent. Okay, cool. So you're quite optimistic, and we'll get into that too, talking about kind of the future of this, I think. But if you'd like to start off your slides, we have some visuals.
Right. So as I start, please, I really want this to be sort of an open discussion. If you guys have questions, we have a system for asking them, and please do come up and chat. Feel free to interrupt me in the middle. I'm going to basically begin with what I'm going to call artificial intelligence, but first of all, there are people who might actually disagree with me on the definition. Beyond that, I'm going to go into some of the modern application space, and if you want to go off track, that is completely fine as well. I've given a number of this sort of lectures on topics like this, and I'm completely happy to chat with you all about whatever you want to go with. So the first interesting thing, and the first thing that I think people might not know, is that artificial intelligence has a really long history of being the next big thing. You can't quite see this. I borrowed this from a report from Team Finland, so I didn't make the plot. However, I'm going to go through it in a little bit of detail. So people are probably familiar with Isaac Asimov's laws. Anybody? Asimov's laws of robotics?
Oh yeah, okay. You're not. Let's see. Don't allow harm to a human being. Don't allow harm to. Don't allow harm to yourself. Well, isn't that the third one?
Yeah. That's basically the three of them are, A, don't harm human beings. B, yes. Obey human beings, and and C, protect yourself. And those things are in absolute order of primacy. And the reason why,
Oh,
yeah.
Sorry. Go ahead.
Oh no, I was going to say this time I'm really letting you go. Go for it.
Okay, I read Asimov's books, and did you, by the way? The
Yeah,
robot
I mean,
series?
I don't think every single one, but yes.
Okay, so like I started reading them after I started becoming familiar with programming, and it seemed like they were conceived as having like sort of contextual human logic, and that's why they could do things like reason about what harm was and what could cause harm and everything. Is that but reading it sounded a little bit unrealistic when I look at what machines are currently capable of. Is it completely unrealistic?
So it's a really astute way to put it, and you're exactly right that it's clear when I say that there's something of issue there, because anything that we do as humans, we tend to debate the underlying principles of. We tend to debate what everything means. What does it mean for some people to come to harm? Well, obviously, in the stories, in the books, the interpretation of that is what causes all the problem. But when I really go and look at it, imagine that it's whatever, the mid 1950s, and someone has said there's this wonderful thing called a thinking machine. I can't do it myself. I'm not that old, but somebody says there's this wonderful thing called a thinking machine, and all we need to do is take what a human being would do and basically make it writ large. I will take, whatever a human being will do and say, in this situation, I would avoid pain. In this situation, I would act in this way. In this situation, I would act in this way. And we really thought, people genuinely thought at the time, that the answer was going to be that there will be a set of deterministic, non-stochastic, by that I mean non-random, non-randomized rules that do not have any dice rolling whatsoever. And in this, I would basically begin from what I see in front of me, and I would be able to deterministically walk through a system of reasoning, basically a tree of logic, to say, well, is this the case? Yes, no. Okay. Is this the case? Yes, no. And eventually I would come down to, what do I do at this exact moment? Now, some of that we still have echoes of today, but as you might imagine, literally doing that for every human situation or every cognitive situation, even for a simple task, turned out to be kind of a non-starter. We can come up with relatively simple sort of subject matter expertise driven rules that say, well, if I'm driving a car, what do I do? But we will quickly, no matter how specific that set of deterministic rules, we will come up against a situation that splits the hair. I mean, this is an aspect of philosophy to say, I'm going to split the hair and I'm going to say, well, what if someone stands the chance to come to harm? What do I do? Asimov says, don't do that thing. Well, what if somebody has a tiny chance of coming to harm? Well, don't do that thing. Okay, what if somebody has a 0.00001% chance of coming to harm? Well, don't do that thing. Well, that's all the time. So now all of a sudden, my system breaks down because my estimation of probability is essentially, infinitesimal but still finite. So what happened, essentially, as a culmination of all this, is we had the thing. This is something that's not widely known, actually, in the current era of AI, called the first AI winter. What's plotted basically on the they say popularity, but what they really mean is funding, right? Because a lot of this is research, the sort of research that I've been doing. And what happened is that all the funding fell out. Sometime around basically the early 70s, people said, you know what, we don't believe you. Public interest waned, government confidence, who were the bulk of the funders, waned, and people, like Asimov, who said, look, by the end of the century, we're going to have thinking machines, were no longer believed. So there was this big dip in popularity.
Was there a specific product that the people were interested in that they didn't get? Like, I feel like right now, the product that the general population is interested in is autonomous cars, and if we don't get that, then people are going to be like, oh, nothing's really possible after all. Was there something like that there?
There sort of was, but ironically, we've been dropping our expectations as time has gone on, which I think is finally going to serve us right. At the time, there were a number of quotes I didn't include in this, but a number of quotes from sort of prominent people, the grandfathers and grandmothers of the field, saying, we're just going to have something that is a general thinking machine. It is going to be generalized. It's going to be exactly like you and me. We're going to be able to reason with it. It's going to, I could say something, wash the dishes, and you understand what that means. And if you don't, you'll ask me a simple question. All the complexities and the vagaries of human. Yeah, exactly. The Jetsons robot, or for that matter, even the Jetsons dog, it would be, enough to do. And it turned out that really wasn't the case. Go ahead.
I was wondering, there's this one very old program. I don't know when it was first came out, but I was introduced to it in the 80s. Bingo. Like this thing here, this thing here was basically, are you talking to another human being or are you talking to a machine? But its answers were so generalized, it's almost like a politician trying to avoid the question kind of thing. But sometimes some of the stuff you would type, you really had to wonder, hey, is that real or what?
Yeah, I will over the course of this talk go closer to what we're doing now. But I actually remember Eliza as well. Again, I'm not that old. I was sort of introduced to technology at a very early age, but at the same time, so Eliza was a program that was partly that was designed to pass. If people are familiar with the Turing test at all, this is something that enters popular media sometimes. Yeah. There we go. So the idea, more or less, is that you put someone in a room and you put someone or perhaps an AI in another room and you let them talk via text. And the question is, I believe, Alan Turing suggested as sort of a thought experiment back in, and I'm trying to remember when he said this, but the idea was, can an AI convince a person that it also is a sentient thinking being? And if so, then potentially it would have all sorts of ethical, moral, philosophical fallout. Like if I can think to the extent that I can come up with creative thought, reductive thought, if I can carry on a conversation with a person, if I can therefore have some kind of internal state that we expect to be indicative of some kind of thought, do I deserve rights? Do I deserve to be? Yeah.
It reminds me, there was a game we played on Endgame, I think a couple times, that was like a reverse Turing test. So we had 2 human players and 1 bot player, and we had to ask the humans and the bot the same question, and the audience had to guess which one was the bot. It was really fun. I don't remember which episode that was. It was good.
And it's a very worthy question. Eliza itself, as I recall, I looked at a basic implementation of it once, and I think it was a combination of stochastically driven questions that it would look for specific words and say, if you said something you didn't understand, it would ask you something that was basically the same question plus a question mark. And
okay, Catapult, and then I have a question.
Yeah.
Go ahead, Catapult.
Okay, my real question was, Eliza was just to bring up what it was, is I'm just curious as to Eliza coming to be and so many people trying Eliza, how much did Eliza sway people to look into AI and develop it just because Eliza opened the eyes and said, what if, people started saying, what if?
So this is actually almost a perfect segue. You'll notice there's several peaks on this plot, right? And as I recall, Eliza was sort of sometime in the early to mid 80s. And it was right in the era of what we called expert systems. So this line that says New Hopes right here might as well be labeled expert systems. So as you notice, I can't, I've said, well, we can't write an exact set of what a human being would do at all the time, even if it has some dice rolling in the middle. Well, we're still not going to get, essentially humans have emergent properties. We have emergent properties, we have nonlinear dynamics that are going on inside ourselves, and we simply couldn't get there by writing down rule after rule after rule. Not even a really good approximation, and that's an important point. So what had happened basically right around here is that researchers working with the limited funds that they had then had come up with a new system, and the new system was called expert systems. Expert systems are essentially a new approach to the idea of AI. They said, well, we still want something that can answer a general question and that can interact with humans. So here's what we're going to do. I will make a database. And in this database, I will put all of the things that are salient to my knowledge. So, to an easy example, if I said, well, rubber bounces, and this ball is rubber, and this ball is blue, and blue things may or may not bounce. And then someone says, here's a blue rubber ball, does it bounce? This is the simplest possible, run. But essentially, you encode all of your knowledge as a database, basically as relationships between objects. And then when it comes time to answer a question, that will basically parse through that system and say, okay, this ball is rubber, rubber bounces therefore. You imagine it's basically making a syllogism if you're familiar with that nomenclature. And they did really very well.
An example of what this kind of expert system, how it was used?
Yeah, and in fact, a lot of these things, you'll notice there's a fall off right here, and we'll talk about that. But at the time, essentially people wanted to answer specifically business questions. So the idea was that people would make systems for business that would answer things like legal compliance issues, for example. Somebody would say, if you're doing your taxes, I will encode the entire things that you need to do with your taxes in terms of a subset of requirements. And then I will parse that, much like you would go and read through the documents to do your taxes, as a separate set of issues that you would then go all the way through and say, have I done my taxes correct, yes or no? And if not, then what do I do next? And you can imagine a system that essentially operates this way, goes through and says, essentially it was an abstraction of the idea of reductionistic rules. It's still basically a set of reductionistic rules. It was deterministic. There wasn't a big stochastic element. There were no dice being rolled. But the idea is that emergence was possible. And by that, in this case, I mean, one could begin with a system that you have and go and interrogate the database until you would come out with, say, the best answer or the correct thing in this case. So business systems actually started to incorporate a lot of this logic through like the 80s. Go ahead.
So what happened here exactly, if it was starting to be really good?
Yeah, so basically what happened here was, as has happened several times, and as I'm going to make the case might be happening now, people made the same claims that they did in the 60s, 50s, and 60s. Basically, the researchers in the area said, you know what? This is how cognition works. Cognition works as a set of knowledge, as interrogated by a set of conditional probabilities as driven by requirements of the current moment. So essentially what I am as a thinking person is I'm just a set of knowledge in a big sack, basically, and I am a set of needs, and those needs basically hit my knowledge and turn into actions. And it turns out that wasn't true. So people, again, made basically the same claim and said, in 5 minutes from now, we're going to have thinking machines that'll do your dishes and drive you to work. And it simply didn't happen. Now, part of that was because of the underlying structure of the models. Part of that was because our computing technology was still somewhat nascent, even though we'd been at it for like 40 years. It still was like highly imperfect. You imagine, what is this, 1987? What do we have at that point? The IBM XT, or like, VIC 20s.
How much RAM did machines have back then?
Yeah, it's not, 64 kilobytes, or some multiple of that, but not very much. And so a lot of the things that we do now are sort of unthinkable with the technology of the 1980s. So essentially it fell out again, and nobody said the term AI in research, occasionally, but like it sort of fell out of popularity again. We had a second AI winter. And one of the things, do not quote me on this, but at this time, somewhere around there, somebody actually came up with the idea of the modern neural net. That is a single layer neural net, which I can describe if people want. Probably that's better for an online conversation, but suffice to say, the idea of modern machine learning, I'll go over this, is the idea that you have a bunch of data about a situation, and then you want to predict one element. And one of the technologies that can be used for that is a neural net. At the time, people thought that those sorts of models were insufficient, that they could not necessarily describe all the situations that they needed to. Oh, thank you. Yeah, that may be more of a next thing. But so essentially, then what? Yeah, that would happen in the early 2000s. Several things happened at once. We had exploding, computer technology and computer capability. And we had a number of mathematical insights that sort of led to what we now call modern machine learning. And I'm going to,
Speaking of mathematical insights, you've mentioned this word stochastic a few times, and you said it kind of means random, but my understanding is that it doesn't just mean random. What does it mean specifically?
So the term random, first of all, comes with some connotations of being uncoupled to an underlying model. So what I mean by stochastic is essentially there are dice rolling somewhere in the process. I'm probably going to do that without thinking about it. So when I say that, what I mean is, there are dice somewhere in the process. If I say, well, the number of cars that you see driving to work in the morning. The number of cars you happen to see has a stochastic element, but it's not purely random. When I say random, people will think, oh, it could be 0 and it could be 1,000,000, and it couldn't be 0 or 1,000,000. There's actually going to be a distribution in there to which there's sort of an implicit die roll. But that process is stochastic, meaning that if I do it again and again and again on days that are otherwise identical, I will still have a variation. There's still a distribution there. Does that make sense?
I think, does that make sense, everyone?
Mm-hmm.
More or less.
I got it.
Yeah.
Okay, so how did we get from here to here? Right. This is one of the hottest elements. This is one of the biggest things that people are looking to do right now. The idea is that a car can drive itself. Now, how in the world? It certainly won't work by the 1950s and 60s technology of I can describe every scenario as a system of yeses or nos, and then I will tell you whether you turn right or left. That clearly fell out. It's clearly also not this idea of an expert system where, if it was the 80s, I'd say, well, I'll just describe all the traffic rules, and all the traffic rules multiplied by a camera image will tell you what to do. Not quite good enough. There's a bunch of things that aren't necessarily described by those emergent situations that we don't expect. So how in the hell are we going to get from this idea of a basically thinking system to something that does a really complex thing like this? And in order to explain that, I'm going to need to start talking about what we used to do when we talked about numerical modeling. So if it is whatever, I'll say 1999, somewhere in there, and somebody says to you, numerical modeling, they're probably talking about a scientific effort. And this is some of what I did, in undergrad and graduate school. That if I say, we're going to talk about, I don't know, we're going to talk about basically artificial intelligence by way of guessing a thing, that we probably mean, my best example is, let's say that we want to know what's going on inside the sun. I come from computational physics. This is a thing we think about all the time. Astrophysics. I want to know what's going on inside the sun, but I can't send a probe to the sun. It's too far away, and I can't, get a probe back from the sun because it's hot and it will melt anything that you put in there. So what I can do instead is I can make a theoretical sun. Well, how do you do that? The sun could have anything. Well, not necessarily the case. What you really do is you get a bunch of people who spent their entire careers making this kind of model. So, I go into one office and I find somebody, and she knows everything about fusion. You know everything about fusion. You've spent your whole career doing fusion. You know how hydrogen, protons and deuterium come together. I go into somebody else's office. He knows everything about gravitation, all the gravitational force and how balls of gas can come together. And somebody else knows about radiation pressure. I get all these people together, and I basically say, I want to make a model of the sun. And they basically tell me all of the extremely specific, extremely complex things that go into a potential sun. And there's probably just a couple of unknowns, things that we call parameters to the model. Let's say in the case of the sun, I don't know quite the overall mass, but I have a range that I can guess. And I don't know the overall hydrogen to helium ratio. I don't know. I don't want to get too deep into how fusion works right now, unless you want to talk about it. But you imagine the idea. There's a couple of what we call free parameters, and everything else is really well declared. So I take my field of experts and I hook them up with a field of computer science experts, and we make us a numerical model where if I put in a total mass and an amount of helium to hydrogen, that I can then run that model forward, and gravitation will make all of the, I simulate a trillion, a trillion molecules. They all fall into each other, they fuse, they make radiation pressure, and eventually from the surface of my hypothetical sun, radiation comes out. Now comes the fun part, where I go and point an actual telescope at the IRL sun, and I get some kind of distribution of photons coming out of it. And now I go and look at my model and I say, hey, are these photons that I expected like the ones that I actually see? And now I start twiddling those couple of open parameters that I had, the amount of helium and the total mass, until what I see in the real sky looks basically like what I expected to see from my model. And then I back out and I say, all right, I made a model with all the best experts. Now what I see in the sky is what I expected to see in the sky. So therefore, those free parameters, amount of helium and total mass, are basically my best estimators for what I think the real sun has. And that was science. That was basically, computational physics, that you would do this sort of thing. But I don't have any of that for this, right? Like, we're in trouble because there's no expert that's going to tell you exactly how to drive a car. And I mean exactly how to drive a car. I can read the driver's manual, but no one can tell me the exact dynamics of like when you push the brake and exactly how much. There is no such expert. So like, what the hell are we going to do?
But we have people, right? Like we have, can we watch people? Can we record them? Is that what we do?
Yeah, exactly. Right. We don't have necessarily like a true expert on like every situation, but we have a bunch of examples. So in the early 21st century, say again?
Is Wikipedia an example?
It could be. If what you want to know is, for example,
he's asking about this person. Do you have like a question? Are you just joining us now?
In a way, but I'm sort of catching on just in like the first five sentences about like the automatic car, but at the same time.
Okay, yeah, we're having a
driving mechanics.
This is a show about the future, and we're talking about machine learning. So please come join us. Mm-hmm. If you have a comment or question, go ahead and stand in the center, like Skeletor here is doing.
Yeah. Although for the moment, the answer is probably yes. That could be an example of what people do. If what the question I'm looking for is like, what would a person say next? Sorry, go ahead, Skeletor. Do you have a question?
Yeah. All right. So you were mentioning things in regards to trying to get something, trying to get what you, how do I put it this way? It's almost like baking. When you are looking to see what you're wanting something to achieve, like for example, you're talking about the sun earlier. You want to find out what's inside of the sun, but you can't find out unless the results that you get back from the sun match what your hypothesis is in a way. Well, with baking, it's very similar, where if you want a certain taste or if you want to get to a certain kind of feel, you have to either, set the parameters of your cooking or your baking to be a certain amount of time, a certain amount of eggs, a certain amount of sugar and stuff like that to find out what the ingredients are that make it to what you've seen coming out and what works for you. So if you had a steak somewhere and you know that steak tastes like this, and you just know that the ingredients are steak, something else, but you don't know in what ways, then that's the way you get the steak. The same thing applies sort of to this, and I know it's an unusual segue into it, but you're trying to accomplish the exact same as a human would do by the parameters that they would try to achieve driving through a city street from one destination to another. But in order to do that, you have to figure out what's making that human. What are the parameters that human keeps going through each time while it's trying to accomplish that. So it's all about finding the parameters per se.
Yeah, so this is an ideal question for the moment. This is sort of the perfect segue because you're touching on the issue exactly. Basically, how do I say, like, if I am baking a cake, let's say that I know eggs and flour and a bunch of other ingredients go into it. I know that there's a temperature. Now, all of those sort of sound like these parameters of what's in the sun. I say, well, eggs, number of eggs, amount of flour, amount of water, all those things. Now I'm starting to define a space. And if I frame the question as being, well, what's the best? You might imagine one thing that I could do is like make a million cakes. I could try that entire space. If you imagine for the moment, wait, where did I just put the...
What are you looking for?
I think I ran over the thing. Okay, yeah. These things I wanted to draw, and I think I might be... Okay, I may or may not make this work, but if you imagine like drawing some kind of a space, in this case, let's say that the only thing in a cake is like eggs, which I'll call E, number of eggs, and proportion of flour or something like this. That you might imagine in the real world, if I could do this a trillion times and do every possible distribution, that there'd be some spot in here that's like the best cake. and there's probably some ISO surfaces as I go out of like, the cake gets worse as I do this. So now the easiest solution, if I have infinity time and infinity resources, is just to make every cake in existence, and I'll just pick the best one. But now the fun begins, right? Because I don't have infinity time and I don't have infinity resources. So what will start is I might guess a spot and go, yeah, there it is. Yeah. And I might also guess some similar spots that are near that. And now in doing that, I've now sampled this sort of region of space, and I can tell that not only is this one the best out of them, but as I go this way, cakes are getting better. So essentially, there are a whole bunch of techniques that, again, if you want to hang out afterwards, we can go after some of these optimization problems that essentially lead me to saying, okay, go this way. And I do it again, and I go here and here and here and here and here. I'm swindling you just slightly on the way that this is done, but we can talk. And the idea is that I do this optimization where I eventually find the very best cake. And I hang on to this idea because this is going to drive almost all of the modern stuff. This idea of saying I can sample, I will eventually arrive at the very best answer. That plus an abstraction that I'll describe in a sec is going to basically drive this. Just a sec. I'm gonna kill that. Okay, yeah. So essentially, come on. Just a sec. Apparently the technology has thwarted me. There
you go.
All right. So this is, if you want, the beating heart of something called machine learning. I haven't said really machine learning before now, maybe a time, but I haven't really dug into it. But the question upon the table was, how in the world are we going to go from a situation where I have experts and they know everything to I don't have any experts, I just have a lot of examples. This is the thing that happened in the 21st century to basically make all of the modern AI, and I'll get to how it works, but basically this is the heart of it. A thing called machine learning. Machine learning is a technique or a set of techniques that we've come up with where instead we use models with a whole lot of parameters, where we start with not a lot of knowledge, but a lot of examples. So to wit, there are probably 2 or 3 ways through this discussion, but I'm going to go with this one. And again, if you want to chat with me, I'm open. But essentially what you do, let us say that I have, this is actually phrased as a classifier, so I'm going to change my example just slightly, if I may. Let's say that I have everybody's age and like their body mass index. And I want to know, does somebody maybe have like pre-diabetes? A bunch of people will show up, maybe they're getting a checkup or something, and let's say there's a test for diabetes that's kind of expensive, but I want to know if I should give that test to this person or that person, or who is basically at high risk. Again, I know very little about diabetes, so this may well be wrong. Please, it's just an example. But so basically I have some axes of information about a person, and if you imagine now creating a space, so let's say that's the BMI on the x-axis, and that's everybody's age on the y-axis. And somebody came and said to me, well, there are some combinations that are sort of more likely to be high risk. As you get older, it's more likely your pancreas can start to go, and et cetera, et cetera. But so what I do, instead of saying, hey, everybody, what's the exact answer to how diabetes works? Instead, the next million people who show up in my hospital, I just give them the test. And now I have what we call a training data set. So in the training data set, let's say all the red dots, does this make any sense if I say, well, here's one stat about a person, here's another stat. That means you and me and everybody live somewhere on this plot. And I put us all down there, and then I color everybody who had diabetes as red, and I color everybody who didn't as blue. So I haven't done any real math yet. I've really just described a space. Now, the machine learning aspect, the idea is rather than having true foreknowledge or true expertise about how it works, now what I have is a set of generalizable models. In this case, there's a line. This is actually what happens if you use a technique called a support vector machine. This is a linear support vector machine. It is literally just you draw a line through the space, and you try to make that line best cut apart red and blue. So this is my machine learning solution. I've literally used these in actual professional systems, so it's not very watered down. This is a real thing that we use. If I say, Here's all the people who had it. Here's all the people who didn't. Now I can lay a line down. Now the fun begins, because if I just put an arbitrary line down, it's likely to not tell me anything. I just say, as you probably remember, a linear line can be defined either by 2 points or by a y-intercept and a slope. People familiar with this at all? That if I draw a line, I can basically use, I can use 2 numbers. So now I have the same as I used to do with my model of the sun. I've got 2 parameters, but now they don't necessarily mean something physical. My 2 parameters are just the y-intercept and the slope. 2 numbers define a line in this space. And what I do is I walk those 2 parameters around. You can imagine any line that could possibly live in this space until, and as I do, I look at what we often call the loss function, which is how wrong this decision surface would be. So, if I took the line and put it all the way down here, you could imagine, well, it's going to say yes to everything. It's going to say everybody has diabetes, and that's usually wrong. Put it up here, it'll say nobody has diabetes. There's some spot in the middle, and usually this is accomplished by a technique we call gradient descent, which might be a little bit ephemeral to the conversation. But again, I'm open to chat about it if you want, until we find the very best line. And as much as machine learning sometimes sounds like an arcane idea, that's it. Basically figuring out the best line. There are a bunch of other techniques. One is, for example, k-nearest neighbors, where I say, if I pick a spot, make an increasing circle until I find 3 or 4 or n neighbors, and then average them. That's another way to do it. There's a bunch of ways to do this. But essentially, the beating heart of supervised machine learning, where by supervised I mean I have tags. It's a deep enough thing that we're not going to get it all in an hour, but this is what normally drives modern predictive algorithms. Is then somebody shows up.
In this example, would the tag be the color, like this person was diabetic, this person was not diabetic?
Yeah, exactly. So here's all the people who had it, here's all the people who didn't. I did my very best to make a single line. And there's other techniques to, you could draw a wavy line or etc. They all basically have parameters. You optimize the parameters until you do the best job of cutting those 2 things apart. Yeah.
Can this be compared also to the is this also how the autonomous driving works? Like, are there any axes here that would work for what would make, does this map to that, or is it more?
It will. There's a high degree of complexity, and I'm going to try and get into it because we're going to talk about something about or something called sorry, not just supervised machine learning, but reinforcement learning, which I will get to in a second. I'm blazing through the topic pretty quick, and that's just by necessity because of time. But okay. Yes, the answer is that basically this fundamental, where I ask a question in the following frame, I have a bunch of examples. And now here's a new scenario. What should I do, or what would a person do, or what is the true outcome? Whatever that question is that I'm asking, I'm essentially answering it by analogy, trying to interpolate / extrapolate / generalize from the data that I've seen to a new spot. So somebody comes into my hospital, this is their stats. Yeah. Go ahead.
For driving, would this be something like, okay, this person put on the brake at this, with these parameters, and this person didn't put on the brake at these parameters? That sort of thing?
Actually, yeah. If you want to think about it that way, there's going to be a high dimensional space. And we'll get there in a second.
So lots of these different graphs.
Yeah, imagine now, I can only plot in 2 dimensions in a trivial way, but actually I guess it's VR. I could have gone for 3. But yeah, if you want, essentially whatever you can enumerate end up on these axes. And then let's say these are all the people.
We've got another axis right here.
Well, sure. Yeah, but imagine this is broad and and so there's all these people. Yeah, in the case of self-driving cars, let's say that I want to think about this in terms of human beings who hit the brake or didn't hit the brake.
Mm-hmm.
And there's going to be an n-dimensional space where n is actually pretty high, but it's the same thing. I have all these places where people didn't hit the brake, and then I have all these places where people did hit the brake. I'm not going to bother, but and essentially now in 3 dimensions, I want to make basically a plane that kind of cuts those things apart. So as this it ascends into higher dimensional space.
Right.
The idea is basically the same. In this case, for a car, it's like, what would a human do? And you're answering, yeah.
Sorry, when it becomes n-dimensional, when there are basically like 10 different factors involved, it's like having just adding more and more axes. Like, even though we can't do that visually, like in the data, that's what we do, right?
Yeah, absolutely. In general, these axes tend to be called features. And the process of figuring out which axes are important and which are not, and or whether or not there's some combination of these that should be used, is often referred to as feature engineering. Do you still have a question? I don't want to leave you out there.
I do. I apologize. Yeah. One of the things that I kept seeing, and I kept wondering myself as I'm looking at this graph, is how do you figure out what is the correlation, or what is the best 2 points of parameters data that you want for correlation? And the second thing I was going to ask, what is your decision boundary? Is it something that can be a plane, or can it be something more of a range where it has a bit of a gray area where it can or cannot? And how do you figure that out?
Let's do the first question first. Like, how do you decide the parameters?
So they're somewhat entangled as questions go. The simplest answer. So this is an aspect of sort of there's a bunch of techniques to do this, but writ large, the idea is partially that you could, whatever model that you're going to use, you would attempt it with a large number of. You remember I said there was a loss function where in this case it's like, how many times would it be wrong? How many blues are over here and how many reds are over here? And I could say, well, since this is just a classifier, have prediabetes, don't have prediabetes, I could say that this line, for example, is wrong like there and there and there. So it's like 3 times out of however many this is. And you could continue to optimize this line until it's wrong the minimum amount of times. Now, this is a little bit more complex than I'm suggesting, but essentially what you do to figure out if features are important is you attempt to use more or less of them, or you attempt, if you have some subject matter expertise, you attempt to make new ones. Let's say I thought the ratio of these was the most important. I could add those. And essentially then you apply your model and see whether or not it gets better.
You try all these different parameters and see if the loss function decreases depending on the different axes you're working with.
Yeah, and now I'm cheating just a little bit, because doing that infinitely means you court a thing called overfit, where instead you're just sort of memorizing. Like, a canonical example is if I let this line be as squiggly as I wanted, I could make a line that like goes up here, then all the I can do it. Obviously, if I say, well, model, you can be whatever you want, then I could end up with something that kind of like does this and go, oh, it's perfect. Look, it's perfect, 100%. Right. But really, probably this is an outlier. Yeah, exactly. Yeah, gerrymandering in data, and you have to really watch yourself for this. There are techniques to get around this. Some of them are called like information criteria. But basically, what you normally do is you pick a handful of this data out and you put it in your pocket. You do your best modeling, and then you throw the data back on and see if it's wrong, and that gives you an idea of whether or not you have overfit. So I guess that's maybe I don't know if I'm getting too technical on that front, but essentially that's kind of what you do to try and figure out. But also, there's model selection. There's a bunch of ways to cut this space up.
For the second question, like he asked if there was like a range. So like, would you use like a range like this, and like how would you
instead
use
of a yes or no, like a binary piece of data? Can it be something that has an analog?
So in general, the answer is yes. I mean, as you can imagine, even writing this is actually true of, if you make a boundary like this, you usually end up calculating, whatever the distance is from the boundary, and then say, that's my confidence that this is in this region or not. So in general, yes, but you usually end up fitting some kind of decision boundary based on moving it around until the loss minimizes. So the answer is absolutely the case. Most of these models in modern parlance, if you're, sitting there and using Python or R to code these up, they will normally come with some kind of probability prediction that actually does take into account like the analog distance here. So yes, Is a simple answer there. Just a sec.
So
go ahead.
Essentially, is that what would be considered creating some sort of simulation of what is happening in terms that we can strictly value as more motivating things to grab versus throw away? Like an axiom of like an axiom of choice, because one option is more valuable than another one, like the 1-0.
All right. So are you asking if we're simulating decision making?
More just the optimization of choice that we kind of do.
Right.
Yeah.
As far as I understand your question.
Yeah. If I understand the question right, then the answer tends to be yes. Normally, for example, I've just said, I've just given you one thing here, but what often happens is, let's say, for example, I've described a binary classifier. A thing is a thing or it isn't. And what you normally do to see whether one of these things works is that you make this thing called a ROC curve, which is short for receiver operator characteristic curve. I don't want to get too deep in the weeds, but I'm happy to if you want, where you basically say, all right, I could, let's say this is the best line I can choose, but actually this is the best slope that I could choose, and I could have been really stringent or really lax about where I put this line. So like I could have put it up here, or I could have put it down here, and in any case, essentially, like, for example, if I was really concerned, and let's say the test is cheap to give people and diabetes is a really big problem, I'll put it all the way down here and go, yeah, we're going to get a bunch of people who don't have it, but we're going to catch everybody who does. Or let's say that it's not so bad, and as long as I get people when they're, at some point it's fine, I'm going to put it way, way up here. So what tends to happen is you make a curve where you plot the number of false positives versus the number of true positives. There's other curves like this, but this is my favorite. And as you can imagine, if I were to put the curve way down here, I would say everybody's got diabetes. And so that means that I catch every single person who has diabetes. Let's say that's one. I catch every single person who has diabetes, but the problem is that I get everybody false positive too. I catch everybody who doesn't have it, and I say they do. So that ends up in a spot sort of up here. Likewise, if I were to stick the thing all the way down here and be like, all the way up here and say like nobody has diabetes ever, then I'm not going to catch anybody who really has it. So that ends up being 0 here. But I also didn't accidentally said anybody had it, negatively. What you would really like is this spot right here where I catch everybody and I don't miss anybody. But what really tends to happen is that you end up kind of with a curve like this, and where that is kind of random. If you were to flip a coin with everybody, you'd get sort of the equal number of true positives and false positives. And generally, then you look at this model and calculate the area under this curve. Sorry, I'm standing in front of it now.
That's calculus.
Yeah, calculate the area under that curve, and you basically go, that area is my best estimate of how well the overall methodology works. I don't know. Is that too in the weeds, or is that helping with the question?
No, that absolutely makes sense. So essentially,
shit, that's really crappy.
Those positive test results and negative test results for all of them, are like for both at the same time. Is that some sort of like simultaneous, like expression?
I mean. If you like,
is that what its operational parameter is? Like that's what it performs for this model. That like kind of like optimization. That this whole thing is.
But basically you're picking a spot. I guess I erased it, but you're picking some spot on that curve that in general corresponds with what you've got. So it's like, if that's the false positives and that's the true detection rate, you basically are really going to have to pick some spot. And normally you do that based on the specifics of the question. So it's like, again, like if this is cancer, right, I want to make damn sure that I catch everybody who has cancer. And so, I want to make sure that the number of true positives is like as close as possible as I can get. So I pick some spot up here where I'm like, I'm going to get at least 97%. And then you just eat the fact that then false positives are like something.
Excuse
So
me.
essentially,
Hey,
We're in the middle of a show.
I'm sorry.
hey, okay, come on in. We're good. What? Okay, so let's see here.
So basically, that curve represents kind of operationally what we need to aim for based off of these parameters.
Yeah. You do your best with the model, and then
Let's answer this question shortly. But if you want to ask more details, we're gonna hang around after the show too to get into more details about. I'm not sure. I think you might be going into more of the abstraction of it than the actual mathematical details, which is interesting. But we should probably move on.
Oh yeah, no, I'm happy. I'm happy to chat after as well. Just a sec. Let me see. Actually, I'm gonna go back really quick and come forward.
Absolutely,
So basically, what I want to motivate, because I'm about to talk about a thing called reinforcement learning, which is a bit of a quantum leap past what I've just done. What I want to motivate is the idea that we have this thing called machine learning, and machine learning essentially exists to give us an answer where we don't have human expertise, but we have a lot of examples. And we essentially say, all right, I want to answer a question. The question is, this is somebody's zip code and their age and their profession, and I want to know how much their income is, or this person's medical stats, and I want to know, do they have diabetes, or anything that I want to answer like that. And you imagine there's a lot of questions that we really want that are more like, here's what my car sees right now, here's what it sees out the rear view, here's what it saw the last second. Do I turn right? Do I turn left? Do I speed up? Do I slow down? And so that's the same kind of question. But now all of a sudden we have an additional degree of complexity in that I want to maybe answer what a person would do. So let me see. What's the best way to go through this? I'll tell you what. Wait, God, I broke it. Okay. So in 1997, Deep Blue beats Garry Kasparov, I think the reigning grandmaster in chess. This blew our minds. I was in college at this time, probably dates myself a little bit, but I went young, so maybe not so much. But and everyone said, and I remember these conversations at the time, sitting around the physics department and such, and going, all right, well, chess is a game that has a lot of variations, but on the other hand, many of the chessboards that you would see in existence don't, add up to an obvious win or loss. So realistically, the number of boards, while still large, is countable and is not that difficult to do. So with technology in 1997, we kind of sort of believed it. But in 1997, everybody said, okay, well, you know what? They are never going to solve the game of Go. People familiar with Go at all?
Vaguely, I don't know how to play it though.
Talk about AlphaGo.
Yeah. I am about to talk about AlphaGo, yeah. So at the time, I remember these conversations. People were like, that is never going to happen. You know what? Machine learning, AI will never do that. That's some things that people will always be better at. It wasn't 20 years before AlphaGo beats Lisadol. Everyone loses their mind about this. And at the time, people, especially people who not necessarily in AI at the time, were like, how in the hell did that happen? The game of Go, it's essentially a board. I couldn't quote you how many rows and columns are on it, but it's a game where somebody puts down blocks. Thank you, yes. And so that is a lot. If you imagine hypothetically, then the number of boards is that you could imagine that exist is something like 3. So a black stone, a white stone, or no stone could be on a spot. It's roughly like 3 to the power of 19 squared, which is enormous. And it ends up being far, far bigger than any computer system we could have. So how in the world did we do this? And that's probably a place to enter the topic of reinforcement learning. So when people ask me about robots, here, let me come over here so I have a bit of a black space. When people ask me about robots,
if you want to.
Oh, can I? Just a sec. Just a sec. I'm gonna do it so I can just write on this. Sometimes people will ask me about robots and like what I think a robot is. And to me, the robot is the brain inside. Whether or not it lives on the internet, whether or not it lives in real space or a simulated space, to me, the robot part is actually the brain in the middle. So what would tend to happen, let's say I'll frame the problem of artificial intelligence vis-a-vis playing a game in terms of the same terms of machine learning. So somebody comes to me and they say, well, here's an awful lot. I'll call this a vector. And this is game state. So haven't done any math yet, but I'm going to get there. Here's a vector with a lot of terms. And let's say that we were playing checkers or something. So it's still a pretty big game. And somewhere in here is whatever, an actual checkers board. It's like one checkers board that you could imagine. And here's another one, and here's another one, and here's another one. As you imagine, this is a really long thing. But checkers isn't an infinitely complex game. So I'm going to put every checkers board that you could imagine, and each one will be one spot in here. It's a pretty long vector. But so essentially, every time that I look at a checkers board, let's say I'm playing checkers, and I look at a checkers board, I can say, yep, this is the one I'm in right now. That's the thing I want to motivate. And then also, I'm going to make another vector. And the second vector, maybe not quite so long, because it's only a matter of n squared, where n is the things, whatever, checkerboard's like 12 across or something, so it's 144 maybe elements.
And this is... You can only be on half the board, so there's only 32 positions that you could be on
great.
Checkers.
Okay, so there's a bunch of these that doesn't. I'm gonna ignore that specific of it for a moment, because the method will actually do it itself. But this is basically my action. And so what's really going to happen is, boy, I sure would like something that goes in between these two things for me. If I'm going to make a robot, the robot is going to have to live in some kind of space in the middle. In fact, I'm going to call this policy. And what I really would like is if this thing said, yep, here's the state I'm in, for it to go, well, here's the move you make. Everything else will be a 0. So how in the world do we get from here to here? Well, one of the first ways that was approached is that you turn this into a matrix. Again, I don't want to spend the world drawing this, so you can probably extrapolate from there. But I turn this into a matrix, and I say, well, if I've played infinity games of checkers, I could tell you that if, just a sec, my handwriting's actually so bad I'm going to screw up the example. Okay. If this is the state that I'm in, this one here, and furthermore, I make this move. So now the number of moves I can make is here. Again, this is basically this sideways. Then I could say, well, if I make this move, I'm 0.1% likely to win the game. And if I make this move right here, I'm 20% likely to win the game, and et cetera, et cetera, et cetera. And now if I had that, which is basically what happened to Deep Blue, I'd be done, right? Somebody would just put a game in front of me, and I'd go, oh, that's the big one. I'll just make that move. But how in the world do I get here? So what really happens, and this generally happens in a simulated environment, is you put people, let's say that I spawn 2 versions of this, or n versions of this, and I tell them to play each other. And furthermore, I start this matrix, since I don't know anything about checkers at first, I start this matrix with like randomness. Whatever, ignore my handwriting, it doesn't matter. The point is I start this matrix off random. And then I have 2 versions of this play each other, and what I do with them is I say, I am going to solve a problem called the exploration-exploitation. I'm not even going to try and write that. The exploration-exploitation problem. Sometimes this is also called the multi-armed bandit problem. The formation of the problem is, imagine you're in Las Vegas, and there's a bunch of slot machines, and you'd like to put money in some of them and see if you can win. You know that they have different rates of payout, but you don't know what they are. Now, you imagine you could just focus on one and see, and like for a long time until you figured out its payout ratio, but that would be ignoring the other ones. And you could sprinkle your time equally across all of them, but then it would take a very long time to learn what they all pay out. What you really want to do is sort of a combination of the two. So what we normally do, or at least the early stage of this sort of thing, is you have these two games playing each other. Each of them, 90% of the time, does the big one. It goes, here's the state that I see. I'm going to use the biggest probability of win. And 10% of the time, it does a random thing. Then we say we play 1,000 games against each other. And after those 1,000 games, I go back and I say, here's all the moves that I made, and here's how often I won. And I reweight this matrix. And gradually over time, I sort of establish what these probabilities really are. And generally, this isn't actually, it's sometimes called the policy, also sometimes Q for the quality matrix. I realize this is getting a little bit arcane, but it's necessary to talk about how cars drive themselves. So I promise this is probably the last bit of math I'm going to do. Are people still kind of comfortable with this, the way that this works-ish? Okay.
I think so. Well, what's a matrix first, real quick?
Oh, so it's an arrangement of numbers, where in this case, one of these boxes says, if I am in this game state, that is the game state corresponding to this row, and I take the action corresponding to this column, that is the sort of payout I expect. And
like
and the sort of yeah, it's basically exactly a table. And let's see, I'm gonna kill that for the moment. Wait, come on. This technology eludes me sometimes.
Well, it's not an exact science.
Well, so now what I've gone over is essentially the way that we make cars drive themselves. The way that we make most modern robots works by this thing called reinforcement learning. And lest you be concerned, reinforcement learning is exactly what I've already said. Basically, you usually have a simulated environment. In that simulated environment, you go and check your quality or policy matrix. You go, here's what I'm going to do. You take that action, you go back to the simulator, and you see, did I win or did I not? And you do that many, many times. And then you go back and sort of reweight your winning matrix by what has happened. Sorry, go ahead.
So actually going back to the grid that you drew earlier, the question I have about it is I started to get into coding a little bit as well, and I was learning about neural networks, and that looked like a more complex neural network where you have multiple different variations of it. The neural networks I'm used to looking at and watching and seeing are basically multi-tiered, where you have a whole row of inputs, like you said, all the different possible boards, and then you have one column that says, okay, well, let's see which the biggest number is by adding all of these different weight lines in, and then you actually take that and do that again, and do that again, and then compress it down.
Actually,
to a couple of
the next slide.
I think just a sec. Do I talk about it? Maybe I don't. Tell you what.
Maybe not. Sorry,
because this is a
real neural network looked like that, right?
Oh yeah. So this is a very valid question. It's actually very useful. So I'm first going to say kind of what a neural network is if people aren't familiar with it, and then I'll go through how they're valuable in this case. So
okay. We are running pretty short on time, by the way. So just
okay. Look, how close are we? Like,
well, it's kind of variable. Time is essentially up, but finish your thoughts and what you wanted to say.
Okay, well, we want to make sure I close out the show, and then we can just keep talking after this. But so essentially, okay, very quickly speaking, a neural net is one of those models where let's say I take everybody's height and weight and age and everything, and I want to know if they have diabetes or something. It's one of these models where I basically say, all of those things that I know live as independent things, and then essentially I am allowed to kind of remix them. Like I'll say, well, I'm going to say that I'm going to make a new thing called hidden variable 1 or something. And hidden variable 1 is going to be like a linear combination of all the things that I know. And hidden variable 2 will also be another different linear combination of all the things that I know, and so on. And this is the simplest sort, but eventually you end up driving all these things down towards a single element, and then that's your decision point. This might be a little bit too weedsy for the current conversation, but suffice to say, a neural net, a deep neural net, in this case the depth is this way, the idea of that there's multiple layers of you doing this. That I haven't described linear regression, but essentially what's going on is I go, if that's A, and that's B, and that's C, and etc., then I'm going to say this is something times A plus something times B plus etc. And these are now the parameters, the things that are cofactors to these. Again, I'm ripping through this, and there's some things that I'm leaving aside, but essentially the idea of a neural net is this. The reason why this is so valuable, partially, is because these have been proven to be able to represent any sort of dynamics in the world that you really want. So they're very valuable for modern things. They tend to take a lot of data to train. But the reason why this is so reasonable is because you remember that policy matrix that I just said, where I said, here's all the boards in the world, and here's all the actions you could take, and in between it's like this board x this action equals this payoff. Well, if I do something like Go, how many Go boards did I say there were? There's like more than the atoms in the universe. This is infinitely big. Well, not infinitely, but it's impossibly big. But what I do is I approximate this matrix with a neural net. And that is the magic that is allowed basically modern AI to operate. A modern autonomous system is AI to operate. I essentially take this matrix and say, yeah, okay, this matrix is going to be, the size of the universe. I can't really keep it in memory, but instead, I'll encode like what's in every part of the Go board. So there's a Go board, and here's a white stone, and there's a black stone, and here's no stone. And I can code that, and I can also take a thing the size of the Go board and say, don't put a stone here, don't put a stone here, put a stone there, and etc. And in between, I put one of these deep neural nets that does the job of asking the question. So basically this is, and again, I think we're probably going to have to end here in a second, but this is the mechanism by which, if I take a car and I say, hey car, you have an image of what you've just seen. I want to feed that in here. You have how good your brakes are. You have like whether or not, how close we are to the waypoint. You have all this stuff, and it's a very large set. I can't possibly encode all the possible differences, but I can shove all of those things individually into a neural net. And out will come, do I speed up, do I slow down, do I turn right, do I turn left? And that's basically the way that we do it.
So with this sophisticated way of narrowing this information into something we can actually work with and everything, it seems really powerful. What to kind of close us out, I guess, do you want to talk about what you think the potential for that is in the future? Where is this headed? What are we going to be able to do?
So if there's one note that I want to close out on, it's basically that this is both a promise and a concern. And the concern is, yeah, thank you. As you might imagine, the promise is pretty well understood. I can take a car and I can make it drive itself. I can take a plane and it can drive itself. I can maybe trade stocks a little bit better than the next person. I can look at an x-ray of you and say, is your bone really broken? And if so, what should we do? Do you have cancer? Do you, have the potential to get a disease later in your life? Are you depressed right now based on what you're writing? All of these things end up being possible with this, but we have to have jettisoned. I don't think we have the video, do we?
Oh, we do, actually.
Okay, cool. We have to have jettisoned. And I'll kind of close on this. So this is a reinforcement learning trained robot. It's in a simulated environment. As you can imagine, the things that we put into it are just where it is right now. It knows where it is. And it knows whether or not it's basically putting torque on its two joints right here. So this is a two-dimensional robot, and it can basically move in any way that it wants. And so we train a model, and we train it to try and have the minimal interaction with this ball. I realize this seems a little abstract for the moment, but bear with me. it doesn't really have any trained behavior at first. So we go through the first couple of generations, we try and train the model first, and the ball just hits it. It just runs through. Nothing that basically the thing trains to is doing any better. But after a while, it starts to get the idea that if it moves away from this ball, that it will get a higher reward. And I'll let you watch. But the idea here is that this little robot develops an emergent set of behaviors. We didn't tell it anything about gravity, for example. We didn't tell it anything about the structure of anything. Literally, all it knows is how much the ball hit it, and is it putting torque on its arms, and where the ball is relative to it. And in doing this, over time, and after quite a bit of training, it starts to get the idea that it can sort of move out of the way of the ball. I say idea, but that's exactly what I want to close on. This thing doesn't really have an idea. It has an internal set of weights that add up to an emergent behavior that, in a couple of these, we'll begin to figure out. There we go. And there you go. So the robot jumps over the ball, or does it? Right? We didn't tell it to do that. We didn't say anything about jumping. We didn't say anything about gravity. We didn't say anything about anything. It just has a set of behaviors inside it that do exactly what we told it to do, which was not touch the ball. And therein lies both the power and the promise. This can do a thing that we didn't know to do. If humans didn't know what jumping was, this thing would have taught us. And yet, if jumping over the ball ends up being a task that is somehow fraught with difficulty. Let's say we didn't expect it to do that. We wanted this to be an industrial robot that like avoids the ball like a snake and rolls over it, and that's what we expected. That wasn't what we were going to get. It would figure out something that we did not want it to do and do that because what we told it to do was avoid the ball and nothing else. Yeah, isn't that kind of cool? This is one of my favorite little reinforcement learning videos. But
now,
basically, this is the issue.
How do you motivate it to avoid the ball in the first place?
So you remember? What? Oh yeah, I can do it.
We're doing a show.
What?
Hey, excuse me, we're doing a show right now. Will you wait until we're done, or go out into the other room? Thank you.
Feel free. Please do. You got it. We can hear you.
Basically, no, I got to turn it on for the stream.
Live streaming too.
So, basically, the way it works, I will drop the camera right here. The way it works is so the ball equals like negative weights. If you touch the ball, you get a negative score. And so, what the object, the creature here is trying to do is trying to minimize its score. Now, one thing you also didn't say, I don't know if you said this or not, in each of these generations, there can be anywhere from 100 to 500 of these objects that all progressively mutate and modify their neural network in different ways. And then, I don't know, you didn't talk about breeding either, but that's another big subject.
This isn't the generation This isn't just a generation of one object. There's like a whole bunch of them here.
This is the best one of that generation, and that it's being shown. And then what happens is like the top half, get.
Hey, that thing doesn't know shit.
This can be.
It doesn't know shit. Not learning.
Yeah, that's what we're talking about.
Yeah, it's basically an emergent behavior.
Okay.
So what Endgame is saying is it can go either way. You can simply train one of these to come up with the best results. You can also train an ensemble of them and essentially allow, if you want to think of the parameter set that is trained in all of them, you can take the ones that perform best on your test and allow them to sort of recombine, sort of reproduce with each other, and then you disallow the ones that do very poorly. So that's sort of a genetic algorithm approach, which is yet another way to do this. I actually don't know whether the authors, this is not mine, I do some other stuff that's like this, but I thought this was really illustrative. I don't know whether the people here actually used a genetic approach or whether they simply trained one for a very large number of epochs. So don't quote me on that. But that's certainly a mechanism by which it's done. And so, yeah, you can say, well, it doesn't truly know anything. It doesn't have a cognition. And you'd be right. This is a very simple thing. All it knows is ball here, me here, what do I do? Oh, the answer is I put torque here and I put torque here. But it has learned that by trying essentially a big ensemble of possible policies, as dictated by there's a deep neural net in the middle of here, and all the parameters in the deep neural net are what are being twiddled. And eventually we arrive at a behavior that ends up being so adaptive to the thing that we asked. So that's basically what I want to close on. Modern AI, we have jettisoned the idea that cognition is going to be the underlying principle. What we now have is emergent behaviors based on how we define a loss function. So the example that I like to use is if I make a car that drives itself, I could say, hey, if you waste a gallon of gas driving around in a circle, that's a negative. But if you hit somebody, that's a huge negative. And now in the old system, I want to say hitting somebody is infinitely negative. The problem is that if I put an infinity into this problem using the modern techniques, the car won't go anywhere. It'll just assume that any probability of ever hitting a person is infinitely bad, and it will take all other negatives and therefore not drive. So now I have the really hard problem of saying, well, how many gallons of gas is a human worth? I want it to be infinity, but it can't really be infinity. So we have to basically set it such that the car actually drives itself and does a good job. And that is, it's a very fraught question. It's the sort of question that we're working out right now. And we want to make sure that basically people are as safe as possible as these techniques with very high power sort of come into the modern era. And I guess I'll leave it there as best I can. Happy to just keep chatting if people want to hang out. But thanks everybody for coming.
Yes.
You want the last word here?
Yeah. And thank you so much, Sean. Really appreciate you joining us and for your expertise. This is this is a lot of really good information that we otherwise wouldn't have anybody to help us with. So thank you so much.
Thank you. Anytime.
All right, I'm going to turn off the security. So if we want to do a group picture, come on up and join us. Let's do one of the slides as our background.
Oh yeah. Okay, take that. Let's see. That one's not bad. That one's not bad. That's okay. You like that? I can go with that one.
Yeah, actually looks pretty decent.
The colorful one is good. I like that.
All right, that's good. Yeah, it's not overwhelming. You know.
All right. What should we? Let's see. Yeah. Yes, definitely. Yeah. No, I like that.
Yeah, totally.
Okay. On three, say. Oh.
Overlords.
Yeah, Overlords.
That's good. On the Overlords. Yay.
Boop. Awesome. Thanks, everyone.
Oh, thanks.
That was nice.
Good picture.
That was a great deal of fun.
Greetings, how you doing, buddy?
What's up, Ken? Long time, man.
Oh, thanks.
Yeah, how you doing?
People coming
Yo.
in.
Oh, been good. Been
She was-
working too much.
yeah.
Working entirely too much.
Roll out.
Oh, bummer.
Hey there, vacuum.
Roll out.
Roll out! Hey!
Oh, it's good to see you again, buddy.
I did see you, man.
want to say one thing. When you're showing
here
the
I can't do
learning
anything.
to jump over the thing, all I can think of is that scene. That strikes me exactly as like how a baby